Hey everybody, Trenton Clark with the Virginia Asphalt Association, and I'd just like to welcome you to our next The More You Know webinar series. This webinar series started back in December of 2023 and is our effort through these webinars to provide you with more information that will help you do your job. Today, we're pleased to have Greg Renegar, Vice President of Engineering for Astec Industries, as our guest in this The More You Know webinar series. So as we go through today, we're going to go highlights, make sure you know how everything works, purpose, get into the presentation itself, and then at the end have time for questions and answers. So if you have never used Zoom before, pretty straightforward. Everybody will be able to type in questions either through the chat or the Q&A portion. And as we go through the webinar, at times we may answer them during the webinar, or we'll hold them to the very end, depending on the question itself. So just make sure as you ask questions, just type them in the bottom and we'll track them, and we'll also have a list of every question that was asked during this The More You Know series. Before we get into it, I'd like to thank our 2024 sponsors of the Virginia Asphalt Association. We'd like to thank those companies in the Diamond Plus, Diamond, and Platinum categories. We want to thank you for your support. It is through your support that allows us to continue to do these types of webinars. What's coming up? Well, we've got another in-person webinar or seminar, but it'll also be hybrid. Be open for VAA members on how taxes can impact your companies, especially those companies that are privately held. We also have our VAA annual meeting coming up. So just a few months in June, we'll be going to the Omni Grove Park Inn in Asheville. So make sure you register. Registration is now open. This October, we got two great events coming up. One is the Scholarship Golf Tournament that'll be held at Mattaponi Springs. Wonderful golf club. If you've never played it before, that information will be coming out soon. Make sure you register yourself or a foursome. And remember, the proceeds go to support the Richard J. Schreck Scholarship and the newly founded Virginia Infrastructure Academy Scholarship. So we hope to see you there on October 9th. And following that, on October 10th, we have our annual discussion with the department in Richmond. So as I mentioned, we're now to that point in our More You Know series where we've got Greg Renegar with Astec Industries. Greg is the Vice President of Customer Success, and in his role, he works with you, the customer, to help make sure that your plants are operating efficiently. And that's what this presentation is on, is what do we need to be doing as plant owners to make sure the plants are more efficient, not only in terms of cost, but also in terms of impacts to the carbon footprint. And there's things that you can do right now to help improve both cost and carbon footprint of your facility. So with that, I'd like to ask Greg to join me. Greg, it's good to see you.
Hey, it's good to be here, Trenton.
Well, what I'm going to do is I'm going to step away, stop sharing my screen, let you pull up your presentation and walk folks through. Again, if you have any questions during this presentation, just stick it in the Q&A section, chat section of Zoom, and we'll answer those questions either during the seminar or during the presentation or at the end. So with that, Greg, I'm going to stop sharing and turn it over to you.
Okay. Hello, everybody. Welcome to the presentation. There are those watching right now who not only believe in man-made global warming, they believe that they have a moral duty to do everything possible to attempt to address this warning. And there are those who watching today who either do not believe in man-made global warming or don't believe that control of global weather patterns are possible at all, who are just sitting on the side, waiting for everybody to come to their senses. And then there's everyone in between those two. But regardless of the truth, there is one thing for certain. There are changes coming to our industry that have the momentum of a freight train barreling down the tracks. The slide shown here, I'm not going to read through all this, but it's just an example of some of the things that are giving all these changes momentum. Now, fortunately, I don't have to have an opinion on this, but it is my job as a manufacturer, as a plant manufacturer, to make sure that the solutions you need in the future are available and affordable. And again, on this slide are some of the drivers that are taking place. Now, we're going to talk about the plan of the future, and we're going to talk about what you can do to your plant now to mitigate some of these changes. First, let's talk about where our industry's been and where it's going in the future. The photograph on the left is from a Warren Brothers plant in 1912. And that's kind of where we started in our industry on the plant side. The middle photograph is a very typical asphalt plant, 2024. And so what's the plan of the future going to look like? Well, let me give you my view on that with this next slide. The automobile on the left is a 1970 Ford Mustang, one of my all-time favorite cars. And the automobile on the right is very recognizable. It's a Mustang too. It's a new Mustang. So as attractive as the one on the left is, they both fulfill the same function, go from point A to point B. But any performance metric that you could possibly measure on an automobile, the new car outperforms the old car. It not only has more horsepower, but at the same time, it has greater fuel efficiency, miles per gallon, higher reliability, better handling, more acceleration, longevity, anything you could measure, it's better on the new car. So what has made the new car, although it looks very similar to the old car, what has made it different? Well, it's technology, the application of technology. So I believe that the asphalt plants of the future will look a lot like they look right now, except the performance will be quite different, just as the old and new cars are with the application of technology. So what does that look like? What does innovation in our industry look like? Well, here's some of the drivers: economics, mixed design, regulation, and competition. And I put regulation in red because right now in the near future, this is going to be likely one of the drivers. So a mixture of those forces comes together and creates a need for equipment. So we combine available technology in a new way, we adapt and we innovate, and it is much like a new recipe. Now, the example I like to give of a new recipe in innovation is Uber. Uber is simply, they took, or three existing technologies were taken and combined together in a unique way. GPS technology, smartphone technology, and software were combined to form a new recipe. The old recipe is, of course, to get from an airport to your hotel is a taxi. The new recipe is Uber. Every day across the world, 21 million people pick the new recipe instead of the old recipe. So that's how innovation works a lot of times. Now, in the asphalt plant process, carbon is produced in three main categories. They're often referred to now these days as A1, A2, and A3, but what it really is, it's what we call upstream manufacturing. It's the production of all the materials it takes to make asphalt, the aggregates and the liquid asphalt. A2 is the transportation. And the third component of the carbon production is A3, the plant operations. Now, if we just take a look at the plant operations, which is exactly what we're going to do today, and look at that by itself, it's the big blue circle in the middle pie chart. And around 90% of the emissions produced by the plant come from the drum or the dryer part of the plant. So that's what we're going to concentrate on. Yeah, there's some things we always want to do with the hot oil system and the burner on the hot oil system and other things that can affect the cost of a ton of asphalt, but the big carbon producer is the dryer. Some fun facts, and I think some of these facts they're very interesting, but I think it's good for everybody from plant operators, plant owners, to the regulators to have a foundation of knowledge about the facts of what it takes to make a ton of asphalt, so that the future makes sense. First of all, 94% of the roads are asphalt. That illustrates the importance of our industry. Basically, no commerce in the United States exists without roads. That's how important they are. And whether it's hot mix asphalt, warm mix asphalt, they all require energy, or they all require heat. We can affect how much heat it takes to make a ton of mix, and a lot of this talk will center around that. RAP, recycled asphalt pavement, is the United States' most recycled material, but on the average, we're only around 21 or 22% RAP is an average of the mix made, and that is opportunity. And our current plant technology can produce mix with from 50 all the way up to 70% RAP, so that's capability. So we have opportunity, we have capability, and there are so many things that could be done now to lower the energy requirements. Now, this is an example I like to use to show how regulation drives innovation. And I'm not saying this is good or bad. I'm just saying this is an example of how that works. In California, decades ago, they basically said they set the NOx levels, and a burner did not exist that could meet that. So people that make burners were forced, to develop that technology. And regulation is kind of the good thing about it, is that in a low bid environment, regulation is the only thing, regulation or specification is the only thing that kind of makes everybody do the same thing. And that's about the only way that happens in a low bid environment. But the bad thing about regulation, every regulation raises the cost of mix, and it affects the smaller producers more than the larger producers. And it also keeps, every time the cost to enter the industry goes up, it keeps new startups out. So that's the good and the bad about regulation. But we live with regulation, and we'll probably be living with a lot more. In the past, our fuel selection was based on the lowest cost fuel and its availability. And we would take our pick from that. In the future, it could very well be that the type of fuel we use is mandated, whether it's natural gas or a hydrogen blend. This has occurred in California for decades. Decades ago, some districts in California, they're concerned about NOx. They said, "Hey, you're going to burn natural gas or vaporized propane, or you're not going to burn anything." And more of that kind of thinking is probably going to come to the rest of the country, a state at a time. And just an example, switching from waste oil to natural gas can result in a 29% reduction in carbon emissions. So which fuel is used does make a big difference. I'm not going to talk too much about hydrogen, burning hydrogen and hydrogen blends, other than if it ever becomes the case that enough hydrogen is available to use to be a viable fuel. We've tested our burners with hydrogen and with hydrogen blends, and we can burn that no problem. The problem is getting enough hydrogen to the plant. The same gas lines and gas line components that work with natural gas don't work with hydrogen. So we're really a long way from that becoming reality. Now, this is a cutaway of a very common top dryer. And we're going to look at, I'm going to use this cutaway to show where the energy from, or the heat from the burner, where it goes in the plant process. So our cold, wet aggregate comes in the left. The hot, dry aggregate comes out. So what happens in the middle? Well, most all of the heat goes into the aggregate, but some of the heat goes into heating up the equipment, and the equipment gets hot, and the equipment radiates that heat to the atmosphere. And some of the heat actually does not get transferred to the aggregate. It leaves the drum in the form of steam and the products of combustion. And the products of combustion is simply a way to describe everything that the burner produces. So we would, in the perfect world at our plant, only the rocks would get hot, but we don't live in that world, so other things get hot. So what we have to do is minimize the heat that goes to the other things besides rocks. So here's how we can do that. You notice that this is another type of drum showing a cutaway of it. And the style of equipment does matter. It can matter. Like in this example here, the drum shell, the little arrows illustrating the drum shell, the heat leaving the drum shell, but it's radiating to an area of the mixing chamber where the mix can absorb that heat. Well, that's good. And we still have heat going into the aggregate. And you notice that the little skinny arrow representing the heat losses in the drum are less. Well, how do we make those less? And in fact, we're going to show you a technology here on the next slide where we can really change how much energy goes into the aggregate and how much we allow to escape. Now, at Astec, we call it the VPAC, but that's just what we call it. I'm going to show you what it really is. So we use computer simulation, and these two drums that are turning, that's the internals of the drum showing how the aggregate is showered through the gas stream, hot gas stream from the burner. Now, what's interesting about this is not like an animation or like a cartoon that maybe an advertising or AI would develop. This is computer simulation. There's millions of calculations being done for hundreds of thousands of particles falling through the air all at the same time. And so we use that technology to develop a geometry of flighting that will give us the showering shown on the right more so than that shown on the left. You can see that there are gaps in the showering over on the left, and those gaps inside the dryer would allow some of the hot gases to pass through there. And we combine that with variable frequency drive. We call it VFD, but variable frequency drive technology. And we put some controls with that. So now we can, by small amounts, speed up our rotary dryer or slow it down and put more energy into the aggregate or less energy into the aggregate. And what that looks like, so we call it a stack temperature control because that's what you're controlling is the temperature of the stack temperature, but you could really think of it as a carbon control because that's what it's really doing. So here's what it looks like at the plant. We sense the temperature at the back house. We sense the temperature at the back house here. That temperature goes to the computer. We have told the computer what we would like the stack temperature to be. It tells the VFD technology whether to speed up or slow down, and that occurs here. And then that we either shower more or we shower less. You think, well, why would we ever want to put less energy in the rock and let more energy escape? Well, that is counterintuitive and it sounds wrong, but we also have a back house here that cleans up the gases from the drum. So we have to operate this back house above the dew point of the atmosphere inside this back house. So there's going to be some virgin mixes to where if we're not careful, we're actually below the dew point and we can mud up this back house. So in that case, we would slow down the drum and allow more heat to bypass to protect our bags. On other mixes, they present real heat transfer challenges, especially aggregates. The composite gradation has a low surface area, like an OGFC type mix. So we might have a very high stack temperature. In fact, so high that we're not only giving away a lot of energy that we purchased, but we may even damage the bags. So in that case, we slightly speed up the dryer. We shower more material per minute because we're turning more times per minute. So we transfer more of the heat to the aggregate and less heat escapes, and we cool off our back house while becoming more efficient. There's some other nuances and benefits of this doing this in this way. We don't have time to go into everything, but that's the gist of it. So, okay, so what is the effect of changing the stack temperature? And when I say stack temperature, that's the jargon we use in this industry, at least here at Astec, for describing the gases that leave the drum. They eventually make their way to the stack, and we just call them the backhouse stack temperature. Well, if we change the stack temperature by 60 degrees, whether we go up 60 degrees or we go down 60 degrees, it'll make about a 10% production rate change in our plant. So if we go down 60 degrees, that means we can make more mix, more tons per hour, more tons per day, and be a more profitable operation. If we change our stack temperature 60 degrees Fahrenheit, it'll change our fuel usage around 4%. That's not a trivial number at all. And the old way to adjust the dryer efficiency, or how much heat goes into the rocks versus how much heat escapes the drum, was to crawl in the drum, usually at night, usually a very warm drum, and either hauling out flights or putting them back in or modifying the flights. And to be honest, it's hard to do that safely. That was the old way. The new way is for the operator to press a couple of buttons in the control house and do that with the VFD drive. It can also make a plant go from 250 to 300 tons an hour, or 250. We've seen all the way up to 350 tons an hour by some other beneficial things that happen. Now, how do we remember this? How do we remember the numbers that I just gave you? You've already forgotten my name. In about a week, you'll have forgotten what day you saw this seminar. In about a month, you'll forget that you even saw a seminar. So how in the world can I get this information in your head? Well, here's what works for me. For some reason, I can remember these three numbers: 60, 10, 4. I don't know why I can remember these numbers. 60 degrees Fahrenheit results in a 10% change in production rate and a 4% change in fuel. That's how I remember it. I hope that memory trick works for you. Okay, this is a photograph of the Fan Engineering Handbook, a classic handbook of equipment designers. It's spread open on my desk. And these are just 2 pages of the formulas. And these formulas are called the fan laws, very famous set of formulas. And they tell us that when you speed up and slow down a centrifugal fan, what happens to the flow rate, or the CFM, cubic feet per minute, what happens to the static pressure that's produced by the fan, and what happens to the horsepower we're required to turn that fan. So what I like to do in these webinars, is we will step through each one of these formulas one at a time and go through each till the participants on this call have a total understanding of each one of these formulas. When I use this slide in person, I can't see your face now, but that's often the look that I get. And it's pretty easy to read minds at this point, and that's how everybody's feeling. So I would never do that. Now, here's all you need to know. For a backhouse exhaust fan, or really any centrifugal fan, if you're turning it at 80% of its full speed, which is like every day almost that you're running, Using VFD technology instead of an outlet damper, so you don't have a damper, you just turn the speed down on the motor, it only consumes 50% of the electrical energy. If you reduce its speed by 50%, such as on a burner fan, which is like every day, it only consumes 12.5% of the energy. Those are amazing changes, and it's part of the magic of using the VFD, variable frequency drives, very affordable, reliable, available technology to take advantage of the engineering behind the fan laws that tell us how centrifugal fans operate. There's a lot of other good things that happen with this. Sometimes your local utility will actually pay for this technology to be used. It creates or corrects power factor of electricity. Your demand charges can be much reduced. There's a lot of other good things that happen. Also, when you slow these fans down, they make much less noise, less worker stress, and happier neighbors. Using the best way I know to explain it is using an outlet damper to regulate, modulate how much CFM comes out of fan would be like driving your vehicle down the road with the accelerator pressed all the way to the floor all of the time and tapping the brake to regulate your speed. Of course, nobody would drive their car like that, but this is just for an example. Whereas using the VFD, variable speed drive, variable frequency drive to speed up would be like you driving your automobile like you really do, mashing the accelerator down to speed up the engine to go faster or slower. Most all new plants get this technology now, but there are not hundreds, but thousands of old plants in the United States that do not have this technology. And it can be added to an older plant. Now, variable frequency drives, that's how they're used on the drier portion of the plant. Another place they're used, and this is not nearly as often, like a drag conveyor, and nothing magic happens like with a centrifugal fan. It basically, we slow the drive of the drag down to where it's only running fast enough to move the production rate coming out of the plant, or all the slats are full. And so what this does, it simply makes the drag on average last about 40% longer. And if you think about it, the longer things wear, the less carbon we're consuming. So that's a good thing too. Now, so what can be done now with other things around the plant? Well, going electric. We can go electric on AC tanks. Of course, it requires new tanks. Hot oil heater. We can heat hot oil with electricity, or we can do away with hot oil altogether. The AC piping can be electric. And there are certain parts of the plant that we must heat, like the drag slat conveyor. The bottom of it is heated on a stationary plant. That can be done with electricity. The bottom of the silo cones are heated. We heat those with electricity. The traverse slat conveyors that transfer the mix to the various silos, they're heated and they can be electrically heated. Actually, what we're seeing right now is that even though in most places electric heat is more expensive than using hot oil to keep plant components hot, we're seeing some of our customers that are owned by European entities. The Europeans are calling over and say, hey, get rid of your hot oil now. We don't care how much it costs, just get rid of it. So we're already seeing that trend occur right now. The AC tank farm, insulating your plant, AC piping, the pipe flanges. We don't even have to think about it. We've known for decades that the return on investment is there. So yes, insulate these things. There are lots of each manufacturer has information out on how many BTUs you lose per linear feet of pipe that's not insulated. that information is out there, but this is one area where you just don't even have to think about it. Now at the dryer, it gulps fuel. You're running 300 or 400 tons an hour, it is gulping fuel. The tank farm is different. It uses very little fuel per hour, but it sips it all day long, all night long, every day of the week. So that's why the insulating this pays off. Now, what about electrification of the dryer? You see, we've talked about AC tanks and vertical tanks, horizontal tanks, and other electricity can be used almost everywhere. But what about the dryer? Well, on a 400 ton an hour plant, what you will find on there is a burner that is rated at 100 million BTUs per hour. Now, it's hard to get our head wrapped around those units because they don't really mean anything to us. Is that a big number? Is that a small number? It's hard to tell. But we can take those units and convert those units to horsepower. And we're more familiar with horsepower. You know, we kind of have an idea of how much horsepower automobiles have, and we know what horsepower is on our drum and on our baghouse exhaust fan, so we know what's big and what's little. So we convert that burner size in BTUs to horsepower. It's not 39 horsepower. It's not 390. It's not even 3,900. The conversion is 39,300 horsepower. Actually, it's an engineering marvel of heat transfer that a burner attached to a rotary dryer can very quickly transfer the amount of energy that would otherwise require a motor this big to transfer. Totally amazing. So I'll just say we aren't there yet on electrified aggregate drying. So, you know, I said before that everything that gets hot on an asphalt plant, besides the rocks, is really a waste of heat, but we don't live in a perfect world, so that's kind of necessary. But we can mitigate that by insulating everything that gets hot, almost. What do you mean by almost? Well, let's talk about the dryer. Should we insulate these dryers? The one on the left is a thermal image that's taken through a special camera where all the temperatures show up as different colors. You probably can't see it, but that little temperature right there is 842 degrees Fahrenheit. So if we were all in a room together, I would ask everyone, it's pretty obvious that that we're losing a lot of heat from this drum. We could be standing 10 feet away from this drum and feel the heat loss on our face. So, you know, I would say, well, it's pretty obvious that we should insulate this drum, right? And most heads were nod, a few hands would go up. And then I would say, well, let's talk about it. In fact, the answer to most any question that can be asked about an asphalt plant, the correct answer is really, it depends. So do we insulate this drum? And the answer that should pop up in your mind is, it depends. So here's what I'm thinking right here. I see 842 degrees. I don't know if that'll be a higher temperature with a different mix design or with a different burner firing rate. I don't know what this drum is made out of. I don't know what material that is, so I can't know the temperature limits of it. So those are some unknowns. Three things that I do know for sure. If we insulate this drum, it will get hotter because the heat can't escape, so that it goes into the metal. It will get hotter. We can no longer measure the temperature of this shell because we've covered it up with insulation. And we certainly can't see any signs of heat damage, heavy scaling or warping or bulging or any of those things. We've covered those up with insulation. So the amount of heat we're losing through radiation here is small, 2, 3, of the total. And those are the bad things that can happen if we insulate it. So that's just my feelings on this subject as an engineer. The drum on the right, actually, this isn't a thermal image. This is just what that drum looks like at night while it's running. And I wouldn't really insulate that one for the same reasons. What I would do if I had a drum that had this situation, I would at least contact the manufacturer or somebody who does work like this and have a conversation about what you should and shouldn't do. So the ductwork. Let me say something about radiation heat loss. When the temperatures are really high like this, the rate of radiation goes crazy because radiation is a function of the temperature of the fourth power. It basically says, hey, you take the absolute temperature and multiply it by itself 4 times, and that represents how much radiation there is at these high temperatures. But when things are not really that hot, like your ductwork, it radiates very little. So is it worth the effort to insulate the ductwork? Most certainly not, especially with the expense and all it would take to do that. But I will say this. It is quite possible that in the future, in order to bid on certain work, certain government jobs, there might be a checklist of items that you have to check off and say you've done these things in order to bid on this work. The ductwork insulation could very well be on there. This is one reason why it's important for industry and manufacturers like myself to be as close as we can be to the discussions with the regulators so that things that really don't move the needle, that cost a lot but don't move the needle, don't become a requirement. So what you're asking, well, why would you say that's a possibility? I was in Australia last year doing our customer schools over there. And after one of the schools, a guy walks up to me with a stack of paper and he says, look, I have to fill out this paperwork in order to bid on certain jobs over here. And it was just page after page of, have you done this? Have you done that? And so that could very well be part of our future. The baghouse, yeah, there's a lot of surface area. It's not that hot, but there is a lot of surface area. So it's certainly not going to hurt. It's not way up in the air. It won't be crazy expensive. So that's probably a good thing to do. And it will probably be a requirement sometime in the future. Now, here's a biggie. Utilizing the storage silos to keep the plant running efficiently. I've got in the next slide or two, I'm going to show you how put some numbers to this. But big efficiency gains are to be made out of not just the equipment itself, but how the equipment is operated. That's a huge thing. In fact, it's a subject all of itself. And of course, you want to manage the silos, the number of trucks, and the production demands. You're juggling all of those balls, but the goal is to keep the plant running. Communicate with your customers, schedule the work, schedule the mixes going from finer to coarser, do midstream on the fly mix changes, do everything in your power to keep the continuous plant running smoothly and continuously. Astec's most successful customers, they don't just use their silos as surge vessels in order to do what I just said. Yeah, they do that. They don't just do that. Our most successful customers use these silos to start each day getting the first round of trucks out, regardless of any plant problems or anything. First round of trucks out. The end of each day is spent filling these silos. Our most successful customers do this. This will minimize plant waste, maximize the quality of the mix. And this is the slide I want to show you. Now, this seems like an outrageous statement. This is not my slide. This is not my information. I borrowed this slide and this information from a colleague and a friend, which I respect a lot. It comes from TJ Young. He manages the operation at Duval Asphalt in Jacksonville, Florida, several plants, and he's consulted for forever with plants all over the world. And he says this, and I believe it: plants that start and stop more than 3 times per shift use up to 20 to 35% more fuel. And I believe that our customers that have the most profitable operations, they keep their plant running all day long. The plants that stop, start, they can have some atrocious drying cost. And so this is important. Now, use as much wrap as possible, do it the right way. Now, right now, if you don't run any more wrap than you run right now, it's due to either specification or wrap availability. And hey, if you don't have it, you don't have it. But where it's limited by specification, I think that the DOTs will be pressured. The DOTs in places where not much wrap is allowed will be pressured to allow contractors to run more. It is incumbent upon our industry to run wrap the right way. What do I mean about the right way? It means the right equipment, the right training, the right best practices, mixed designs that are great. Buzz Powell and Randy West have proven the 2009 NCAT test track results, 50% wrap and using warm mix technology can not only be the most economical mix, but it won the award of the one that lasted longest on the test track. When you look at a 30,000 ton pile of wrap, your mind should convert it to 70 6,000 gallon transport trailers of virgin AC, because that is what it replaces, and 28,000 tons of clean aggregate. And, you know, we're entering a world where the EPDs, environmental product declarations, like a nutrition label for each mix will be required. And wrap is basically like a free pass on that. The more wrap you can use, the better off you are in that area. Hey, a lot of places, the aggregate that comes off the road is the best aggregate available. There's some places that import aggregate from as far away as Nova Scotia. They just don't have good local aggregates, and the best aggregates they will ever use are those which are milled up off the roads. Now, you know, I talked about places that don't have enough wrap to really increase the percent wrap. There are some places in our country where excess wrap is a real issue. In fact, there's some places that have not thousands, but millions of tons of wrap stockpiled. It's a shame. Now, so what can we do about that? Well, there is a product, we call it CCPR, Cold Central Plant Recycling, and it's basically a 97% wrap product that has no burner, no heat is added. A little bit of water may be added as a compaction aid. Approximately 2% AC, maybe 1.5% cement. And it doesn't replace hot mix, but is a product that uses 97% wrap that can be used in addition to hot mix. So what I'm talking about, Walmart parking lot. So instead of somebody else putting down 8 inches of a rock base, you, the asphalt producer, produce 5 inches of CCPR and get that part of the work. And that's a great way that we can utilize the wrap that's stockpiled around our country. Again, this is a whole subject by itself. I'm just going to throw it out there. Warm mix asphalt. I say just do it. Yes, you can. You know, there's few things that get as much pushback as this. And I want to tell a story about Tim Boone, Napa member. He told me this story at a Napa meeting. Tim Boone runs Nashville Asphalt plant in Virginia. 100% of their business is FOB. And they do not make 1 ton of mix over 260 degrees Fahrenheit. And if they do, they're surrounded by multi-million-dollar houses, and their permit would just disappear if they had any smoke or odor coming from their plant. And they've also demonstrated to their customer base it is not just as good, it's better than what the smoky mix they were getting before. So if Tim Boone can do it in Virginia, you can too. It's coming sooner or later anyway. This is kind of a famous photograph that was taken in the summer of 2007 at a local plant in Chattanooga. And this is the first day that we ran 50% wrap with foam warm mix. And here's what their conventional mix look like. Basically the mix they make almost every day of the week. And this is what the warm mix look like. And if you run the numbers thermodynamically, if you lower the mix temperature 50 degrees Fahrenheit, it results in about 11% less fuel. We actually hear about contractors that use a lot more less fuel than that, than 11%. Don't really have an explanation from it, but people report those things. But thermodynamically, I can't say anything more than 11% less fuel. This is going to be part of our future. You guys will be telling your kids and grandkids about the days where everybody ran mix that was so hot it smoked and you could smell it forever. And those days are going to be coming to an end. You know, Astec pushed the water foam technology, but there's other chemical solutions that work just fine. So basically what I'm saying is, hey, pick a solution and use it. Don't just use it as a compaction aid, which is what most folks do now, but use it to actually make your mix at a low enough temperature where you don't have the smoke or smell. And I mean, that was the reason in 2007 when it first gained a lot of attention, but now it's the 11% less fuel. Stockpile technology or management, moisture management, and stockpiles is something that you rarely see in the United States. If you could visit any plant in Europe or Australia, you will see all the materials covered like this or in some way. We have a few customers that do their version of this. I don't have these slides in this presentation, but again, our most successful customers, they don't always have the newest equipment, the best burners, and all of that stuff, but they have storage silos that they store mix in and start the day out with mix, and they manage the moisture in their stockpiles. And those customers are our most successful customers. We have a 2%, in some areas, a 2% reduction. It can be done by stockpile management, pave and slope the stockpiles. And that knocks 21% off the energy requirement. Huge numbers. Your plant production rate goes crazy in a good way. Now, as we kind of draw to a close, here's that A1 and A2 and A3 that we talked about. We're not going to change the A1, the material carbon that we encounter. We're not going to change the transportation. We're just going to change some things that happen at the plant. And look what happens to the numbers. We're going to start with a baseline of an asphalt plant using number 2 fuel. Then we just switch to natural gas. And our carbon goes down 9%. Or you could say your fuel usage goes down. Well, the carbon production, same amount of heat, but less CO2. Now, if we use natural gas, we pave and slope the stockpiles, and only half of the mix that we make is made at a reduced temperature. Now we're down 20% from the baseline. If we use natural gas, pave and slope our stockpiles, all of our mix is warm mix, and we use a 20% blend of hydrogen, which is like easy. And in some places it's done now. Now we're down 26%. So, you know, there's not going to be an equipment silver bullet to be like to make all the carbon go away. But there are several easy things that can be done and that will be done, that we will be forced to do, that will significantly drop the carbon output of an asphalt plant facility. And we hadn't even touched the materials or the transportation yet. So what will the plan of the future look like? It might look something like this, in that it's all inside. This is a plant of ours in France, 2013. And we're going to look inside that building on the next slide. But this is where the cold feed bins are across here. And inside the building, that's what the cold feed look like on the from the inside of the building. This is the double barrel inside. And that's a pretty normal thing. This is photographs I took in Sydney, Australia last number of a Fulton Hogan plant. The plant is here, the silos are here, and that's the drag conveyor going from the plant to the silos. And over here on the right's a little video clip I'm going to play for you. And that's just me standing there with my smartphone, videoing the plant and turning in a little circle. And this is not always done in Australia. This is not always done in Europe, but in a lot of places this is done. This was an industrial park where basically all the manufacturing facilities look like, you know, just big boxes. So if they make the asphalt plant look like that big box too, nobody has a problem with it. So what might the future look like? The plants are going to be very quiet. There are going to be no odors or visible hydrocarbon emissions. We can accomplish that now by spending a fortune on blue smoke remediation equipment, or we can just make warm mix, which costs less to make, and we won't have any odors or visible hydrocarbons. The plant's going to be more fuel efficient, mostly electric components, covered or partially covered facilities. What will the future look like? The critical components on the plant, the reducers and the big bearings and the things, the expensive things that can shut your plant down and that are hard to get, they will have condition monitoring on them so that we can anticipate when a maintenance needs to occur. There'll be real-time energy use monitoring. There are going to be technologies that really minimize waste at the plants. They assist the operators, and basically it makes a mediocre plant operator into a great plant operator. And so we're going to see a lot more wrap. We're going to see a heck of a lot more warm mix asphalt. We're going to see more wrap bins than we've had, so that we can control the higher wrap mixes, higher recycle. Alternative fuels, we're going to see the application of technology. These plants are going to have less impact. We're going to be better neighbors. And I want to end with a plug from a recent publication from Napa. And my buddy TJ Young authored this. And it's this is the cover sheet, or the cover of it, Production Strategies for Saving Money and Reducing Emissions. And it is one of the most well-done papers on this subject I've seen. These are the topics that are covered. I've kind of touched on some of them, but they're covered in more detail here. And it's an excellent write-up. Now, here's what's unique about this, is TJ produced these sheets, self-audit worksheets that one can take, walk around the plant, fill in some blanks on this, add up some numbers, and decide what makes sense to do and what doesn't. From stockpile management, dryer efficiency, VFD exhaust fan hot oil system, it just makes it easy to take the go from an abstract theory into an action plan that makes sense on the plant. Hey, I'm Greg Renegar with Astec Industries. I spent 38 years in engineering, but the past couple of years, it's been my job to help our customers be successful. That's my contact information on the bottom of the slide. If I would love to help your operation become more successful, so give me a call and we'll get to work.